Now that we understand what is deterministic encryption, let's see some constructions that provide security against deterministic chosen plaintext attacks. So first, let me remind you that deterministic encryption is needed, for example, when encrypting a database index, and later we want to look up records using the encrypted index. Because the encryption is deterministic, we're guaranteed that when we do the lookup, the encrypted index is going to be identical to the encrypted index that was sent to the database when the record was written to the database. And so this deterministic encryption allows us a very simple and fast way to do lookups based on encrypted indices. The problem was that we said deterministic encryption can't possibly be secure against a general chosen plaintext attack, because if the attacker sees two ciphertexts that are equal, it learns that the underlying encrypted messages are the same. So then we define this concept of deterministic chosen plaintext security, which means that we have security as long as the encryptor never encrypts the same message more than once using a given key. In particular, this key comma message pair is only used once. For every encryption, either the key changes or the message changes. And then, as I said, formally we define this CPA, deterministic CPA security game, and our goal in this segment is to actually give constructions that are deterministic CPA secure. So the first construction we're going to look at is what's called SIV, synthetic IVs, and the way this construction works is as follows. Imagine we have a general CPA secure encryption system. So here is the key and here is the message, and I'm going to denote by R the randomness that's used by the encryption algorithm. Remember that a CPA secure system that doesn't use nonces has to be randomized, and so we're explicitly going to write down this variable R to denote the random string that's used by the encryption algorithm as it's doing the encryption. For example, if we're using randomized counter mode, R would be the random IV that's used by randomized counter mode. And of course, C is the resulting ciphertext. Now, in addition, we're also going to need a pseudo-random function f that what it does is it takes arbitrary messages in the message space and outputs strings R that can be used as randomness for the CPA secure encryption scheme. So the little r over here is actually a member of the big R set. Okay, and we're going to assume this is f is a pseudo-random function that maps messages to random string. Now the way SIV works is as follows. It's going to use two keys K1 and K2 to encrypt the message M. And what it does is the first thing is going to apply the pseudo-random function f to the message M to derive randomness for the CPA secure encryption scheme E. And then it's going to encrypt the message M using the randomness that it just derived. And this is going to give us a ciphertext C, and then it's going to output this ciphertext C. Okay, so that's how this SIV mode works. Basically, it first derives the randomness from the message being encrypted, and then it uses this derived randomness to actually encrypt the message to obtain the ciphertext. Now, I'd like to point out, for example, if the encryption scheme E happened to be randomized counter mode, then the randomness R would just be the random IV, which would actually be output along with the ciphertext. So this means that the ciphertext is a little bit longer than the plaintext. But the point here isn't to generate a short ciphertext. Rather, the point here is to make sure that the encryption scheme is deterministic. So if we encrypt the same message multiple times, every time we should obtain the same ciphertext. And indeed, every time we'll obtain the same randomness R. And as a result, every time we'll obtain the same ciphertext C. So it's fairly easy to show that this encryption scheme really is semantically secure under a deterministic chosen plaintext attack. The reason that's so is because we apply the pseudo-random function f to distinct messages. Well, if we apply f to distinct messages, then the random string that f generates is going to look like just truly random strings, a different random string for every message. And as a result, the CPA secure encryption scheme E is always applied using truly random strings. And that's exactly the situation where it is CPA secure. So because these R's are just random indistinguishable from random strings, the resulting system is in fact going to be CPA secure. So this is just the intuition for why this works, and it's actually fairly straightforward to actually formalize this into a complete proof. Now I should emphasize that this is actually well suited for messages that are more than one AES block. In fact, for short messages, we're going to see a slightly different encryption scheme that's actually better suited for these short messages. Okay, now the really cool thing about SIV is that actually we get ciphertext integrity for free. In fact, we don't have to use a special MAC if we want to add integrity. In a sense, SIV already has a built-in integrity mechanism. And let me explain what I mean by that. First of all, our goal is to build what's called Deterministic Authenticated Encryption, DAE, Deterministic Authenticated Encryption, which basically means deterministic CPA security and ciphertext integrity. Remember, ciphertext integrity means that the attacker gets to ask for the encryption of messages of his choice, and then he shouldn't be able to produce another ciphertext that decrypts to a valid message. Okay, so I want to claim that in fact SIV automatically gives a ciphertext integrity without the need for an embedded MAC or anything else. So let's see why. In particular, let's look at a special case of SIV when the underlying encryption scheme is randomized counter mode. Okay, so we'll call this SIV-CTR, again to denote SIV, where we're using randomized counter mode. Alright, so let me remind you again how SIV works in this case. Well, so we take our message, here we take our message, and then we apply a PRF to it, and that derives an IV. And then that IV is going to be used to encrypt the message using randomized counter mode. Okay, so in particular, we're going to use this PRF FCTR for F counter for randomized counter mode, and essentially we evaluate this FCTR at IV plus 1, up to IV plus L, and then we XOR that with the message, and that gives us the final ciphertext. Okay, so this is SIV with randomized counter mode. Now let's see how decryption is going to work, and during decryption we're going to add one more check, and that's going to provide ciphertext integrity. So let's see how decryption is going to work. So here we have our input ciphertext, so it contains the IV and the ciphertext. Well, the first thing we're going to do is we're going to decrypt the ciphertext using the given IV, and that will give us candidate plaintext. Now we're going to reapply the PRF-F from the definition of SIV to this message. Now, if the message is valid, we should be getting the same IV that the adversary supplied as part of the ciphertext. If we get a different IV, then we know that this message is not a valid message, and we simply reject the ciphertext. So this is really cute. It's a very simple kind of built-in check to make sure that the ciphertext is valid, right? We simply check that after decryption, if we rederive the IV, we would actually get the correct IV. And if not, we reject the message, and I claim that this simple check during decryption is enough to actually provide ciphertext integrity, and therefore deterministic authenticated encryption. So I'll state this in a simple theorem, basically to say that if F is a secure PRF, and in counter mode that's derived from FCTR is CPA secure, then the result, in fact, is a deterministic authenticated encryption system. Now, the proof for this is not too difficult. In 2 sentences, let me just show you the rough intuition for why this is true. So all we have to argue is just ciphertext integrity. So we already argued before that the system has deterministic CPA security. All we have to argue is just ciphertext integrity. So to argue that the system has ciphertext integrity, let's think again how the ciphertext integrity game works. Adversary asks for the encryption of a bunch of messages of his choice, and he gets the resulting ciphertexts, and then his goal is to produce a new valid ciphertext. Well, if that valid ciphertext, upon decryption, decrypts to some completely new message, then when we plug this new message into the PRF-F, we're just going to get some random IV, and it's very unlikely to hit the IV that the adversary supplied in the ciphertext that he output. So therefore, that says that when the adversary outputs his forged ciphertext, the message in that forged ciphertext basically should be equal to one of the messages in his chosen message queries. Otherwise, again, the IV that you get is simply not going to be equal to the IV in the forged ciphertext with very high probability. But if the message is equal to one of the messages that the adversary queried us on, well, then the ciphertext that we're going to get is also going to be equal to one of the ciphertexts that we supply to the adversary. But then his forgery is simply one of the ciphertexts that we gave to him, and therefore this is not a valid forgery. He has to give us a new ciphertext to win the ciphertext integrity game. But he gave us one of our old ciphertexts. So this is the rough intuition. I hope I kind of went through it quickly. I hope it kind of makes sense. If it doesn't, it's not the end of the world. I'm going to reference the paper that describes SIV at the end of the module, and if you want to see this in more detail, you can read and take a look inside of that paper. But regardless, this is a very cute idea that I wanted to show you, where kind of the fact that we derive the randomness for deterministic counter mode using a PRF also gives us an integrity check when we actually do the decryption. Okay, so this SIV is a good mode for doing deterministic encryption when you need to, particularly if the messages are long. If the messages are very short, say they're less than 16 bytes, in fact, there's a better way to do it, and that's the method that I want to show you now. So the second construction is actually trivial. All we're going to do is we're going to use a PRP directly. So here's what we do. So suppose ED is a secure PRP, so E will encrypt and D will decrypt. And I claim that if we use E directly, that already gives us deterministic CPA security. So let me show you very quickly why. So suppose f is a truly random invertible function from x to x. Okay, so remember, a PRP is indistinguishable from a truly random invertible function, so let's pretend that we actually do have a truly random invertible function. Now in experiment 0, what the attacker is going to see, well, he submits a bunch of messages, the messages on the left, and what he's going to see is basically the evaluation of f on the messages on the left that he supplied. Well, in the deterministic CPA game, all these messages are distinct, and so all he's going to get back are just q distinct random values in x. That's all he sees. Yes, just q distinct random values in x. Now let's think about experiment 1. In experiment 1, he gets to see the encryptions of messages on the right. Okay, the M11 to MQ1. Well, again, all these messages are all distinct, so all he gets to see are just q random distinct values in x. Well, these two distributions in experiment 0 and experiment 1, therefore, are identical. Basically, in both cases, what he gets to see are just q distinct random values in x. And as a result, he can't distinguish experiment 0 from experiment 1. And since he can't do this for a truly random function, he also can't do this for the PRP. Okay, so that explains why directly encrypting with a PRP already gives us a CPA secure system, very, very, very simple to use. That says that if all we want to do is encrypt short messages, say less than 16 bytes, then all we need to do is just directly encrypt them using AES, and the result will in fact be deterministic CPA secure. So if your indices are less than 16 bytes, directly using AES is a fine thing to do. Notice, however, that's not going to provide any integrity, and we're going to see how to add integrity in just a minute. But the question for you is, what do we do if we have longer than 16-byte messages? Well, one option is to use SIV, but what if we wanted to actually use this construction too? It's actually an interesting question. Can we construct PRPs that have message spaces that are bigger than just 16 bytes? If you remember, in the past we constructed PRFs that had large message spaces from PRFs that had small message spaces. Here we're going to construct PRPs with large message spaces from PRPs with small message spaces. So let's see how to do it. So suppose ED is a secure PRP that operates on n-bit blocks. There's a standard mode called EME that actually will construct a PRP that operates on capital N-bit blocks where capital N is much, much bigger than little n. So this would then allow us to do deterministic encryption on much larger messages than just 16 bytes. In fact, it could be as long as we want. So let's see how EME works. It's a bit daunting at first, but it's not a difficult construction. So let's see how it works. So EME uses two keys, K and L. And in fact, in the real EME, L is derived from K. But for our purposes, let's just pretend that K and L are two distinct keys. The first thing we do is we take our message X and we break it up into blocks. And then we XOR each block with a certain padding function. Okay, so we use the secret key L to derive a pad using this, function P that I'm not going to explain here. We derive a different pad for each one of the blocks, and we XOR that pad into the block. The next thing we do is we apply the PRP E using the key K to each one of these blocks, and we're going to call these outputs PPP0, PPP1, and PPP2. The next thing we do is we XOR all these PPPs together, and we call the result MP. Actually, this XOR doesn't need to be there. And we call the result of this XOR MP. The next thing we do is we XOR all these PPPs together, and we call the result MP. We encrypt this MP using E and the key K, and we call the output of this encryption MC. Okay, so then we XOR MP and MC, and this gives us another key M, which we use to derive one more pad, and then we XOR this output of this pad with all the PPPs to get these CCCs. Now we XOR all these CCCs together. That gives us a value CCC0, which we then encrypt one more time with all these E's. We do one more padding with all these P's, and that actually finally gives us the output of EME. Okay, so like I said, this may look a little daunting, but in fact there's a theorem that shows that if the underlying block cipher E is a secure PRP, then in fact this construction EME is a secure PRP on this larger block, 0, 1 to the capital N. The nice thing about this construction is you notice that it's very parallel, and actually that's why it's a little complicated. Kind of every block gets encrypted in parallel, so if you have a multi-core processor, you can use all your cores to encrypt all the blocks at the same time. And then there would be one kind of sequential step to compute this checksum on all the outputs, and then one more parallel round to encrypt one more time, and then finally you get the outputs. These function P's, by the way, that generate the pads are very, very simple functions. They take constant time, so we're just going to ignore them in terms of performance. So the bottom line is performance here, you notice, requires 2 applications of E per input block. And it turns out this can actually be slower than SIV. If SIV is implemented properly with a very fast PRF to derive the randomness, then in fact SIV can be twice as fast as this particular mode of operation. For this reason, I say that the PRP construction is very good for short messages, whereas SIV is good if you want to encrypt longer messages in a deterministic fashion. But now what if we wanted to add integrity to this PRP-based mechanism? So can we achieve deterministic authenticated encryption using the PRP mechanism, where we directly encrypt the message using a PRP? And it turns out the answer is yes, and it's actually, again, a very simple encryption scheme that you should know about. Basically what we're going to do is we're going to take our message and we're going to append a bunch of zeros to this message, and then we're going to apply the PRP, and that's it. And that's going to give us the ciphertext. Now, very, very simple. Just append zeros and encrypt using a PRP. When we decrypt, we're going to look at these least significant bits of the resulting plaintext, and if they're not equal to 0, we're just going to reject the ciphertext. And if they are equal to 0, we're going to output the message as valid. Okay, so that's it. That's the whole system. Very, very simple. Simply append zeros during decryption, and then check that the zeros are there when you decrypt. And I claim that this very simple mechanism actually provides deterministic authenticated encryption, assuming, of course, that you've appended enough zeros. In particular, if you append n zeros, we need 1 over 2 to the n to be negligible. And if so, then in fact, this direct PRP-based encryption, in fact, provides deterministic authenticated encryption. So let me see why. Well, we already argued that the system is CPA secure, so all we have to argue is that it provides ciphertext integrity. And again, that's easy to see. Let's look at the ciphertext integrity game. So the adversary is going to choose, let's say, a truly random permutation, so a truly random invertible function on the input space. In this case, the input space is the message space and the n0 bits. And now what does the adversary get to do? Well, he gets to submit Q messages, and then he receives the encryption of those Q messages. Namely, he receives the PRP at his chosen points concatenated with n zeros. Okay, that's what it basically means to query the CPA challenger. So in case of a random permutation, he simply gets to see the value of this permutation at Q points of his choice, but only concatenated with n zeros. And now what's his goal in the ciphertext integrity game? Well, his goal is to produce some new ciphertext that's different from the ciphertext that he was given, that's going to decrypt properly. Well, what does it mean that it decrypts properly? It means that if when we apply pi inverse to the ciphertext C, it had better be the case that the n least significant bits of C are all zeros. And the question is, how likely is that to happen? Well, so let's think about this. Basically, we have a truly random permutation, and the adversary got to see the value of this permutation at Q points. How likely is he to produce a new point that, when inverted, happens to have n zeros as the least significant bits? What we're doing here is basically we're evaluating the permutation pi inverse at the point C. And since pi inverse is a random permutation, how likely is it to have its n least significant bits be equal to 0? So it isn't hard to see that the answer is, at most, the probability is at most 1 over 2 to the n, because again, basically the permutation is going to output a random element inside of x times 0, 1 to the n, and that element is going to end with n zeros, but basically with the probability 1 over 2 to the n. And as a result, the adversary wins the game with negligible probability because this value is negligible. So that's the end of this segment. I wanted you to see these 2 very cute deterministic authenticated encryption schemes. The first one we called SIV, where say you would use randomized counter mode and you just derive the randomness for randomized counter mode from a PRF applied to the message. And the very cute idea here is that during decryption, you can simply recompute the IV from the decrypted message and verify that that IV is what's given to you in the ciphertext. And that simple check is actually enough to guarantee authenticated encryption, or rather deterministic authenticated encryption. So this mode is the way you would encrypt an index in a database if the index was large. If the index happens to be short, maybe say it's 8 bytes, if it's an 8-byte user ID, then you can directly use a PRP, and the way you would do it is you would append zeros to those 8 bytes, and then those zeros would then be used as an integrity check when you decrypt. And again, if you are able to append enough zeros, then in fact this also provides deterministic authenticated encryption. As an aside, I showed you that there's a way to build a wide block PRP from a narrow PRP, and that particular mode of operation is called EME. So we're going to refer to EME actually in the next segment.